Hi, I'm Shanaz. In this lecture, we are going to characterize the finite p primary abelian groups with d g equal to 1. So we are going to classify all finite p primary abelian groups g with dg is equal to 1. So let us recall we have defined this dg to be equal to the dimension of this vector space G mod PG. So G mod PG over some finite field, say FP. The field FP is, this can be this field as well. I mean this dimension of this vector space over this field, this is defined to be equal to dg. So all groups with dg equal to 1, we are going to characterize all such groups. Now before we proceed further, let us recall the correspondence theorem. Correspondence theorem. So this theorem states that if G is any group and N is a normal subgroup of G, then we have this map from G to G mod, and this is the natural map or canonical map. So this is a map pi which takes pi from G to G, which takes an element which carries out this element to its coset. So this element A goes to the coset of N determined by this element A. So if this is the top search result. This is indeed a homomorphism, a surjective homomorphism. So this theorem states that suppose we have the family, say, so let us denote the family of subgroups of G which contain N by this notation. So this is the family Hn, that is all subgroups H of G that contain N. And let say this F be the family of all subgroups of G. G mod N. So this is the family of all subgroups of G that contain N. So this contains the subgroups of G that contain N, and F is the family of all subgroups of G mod N. Then this theorem states that there exists a one-to-one correspondence between these two sets. I mean, if we have any subgroup, say K of G mod N, then corresponding to this subgroup K, we have a subgroup H of G that contain N. So this is the correspondence theorem. Now we are going to use this theorem in the following lemma. So we have this lemma here. So if G is a finite p primary abelian group, this is a finite p primary abelian group. then d of g is 1 if and only if g is a non-zero cyclic group, is a non-zero cyclic group. So we have to prove if G is a finite p primary abelian group, then this dg is equal to 1 implies that G is non-zero cyclic group, and if G is given to be a non-zero cyclic group, then dg is equal to 1. So let us prove this. So let us prove first this direction. So we are going to assume that G is a non-zero cyclic group. So let G be a non-zero cyclic group. Then now we know that if G is cyclic group, then the quotient group of G is also cyclic. Then so is any non-zero quotient group of G. So if every quotient group of G is cyclic, so in particular this group, I mean G mod PG is also cyclic, is cyclic. Now one can note here this G mod PG is non-zero. So if this G mod PG is 0, this means this G is equal to PG. Now this thing is true only if either G is 0 or G is infinite group, but G is given to be non-zero, so this is not true. So if G is infinite, this can be true, but G is also given to be finite, so G is never gonna be equal to PG. So if G is not equal to PG, this quotient over here, this is never 0. Now there are groups for which, suppose there are groups for which H is equal to pH. In fact, such groups are infinite, and we can provide here an example of such a group. So these groups are called Pfeffer groups. So they are called Pfeffer groups. So actually they are the subgroups of the infinite cyclic group C. So actually, so these groups are defined as Z of p to the power infinity. So this is actually a subgroup of C infinity. This is a subgroup of this group. This is a multiplicative group of non-zero complex numbers. So this Zp infinity, this is actually the cyclic group Zn, which is same as so this group contains all those complex numbers which are of the form 2 pi I say over p power n. where this n is bigger or equal to 1. One can note over here this complex number, this lies on the unit circle. So for each n, for every integer n bigger or equal to 1, the subgroup Zn is the unique subgroup of Zp in infinity. So it is like this. So first we have the trivial group when this thing is 0 here, so this is 1, this is contained in Z1, I mean when this n is equal to 1, so this is proper containment. This is contained in Z2, I mean when we have p square here, and similarly this chain goes on, and finally we have this infinite cyclic group Zp in infinity. So this Zp in infinity is such that each of it is a p primary component is isomorphic to I mean Zp in infinity is isomorphic to p primary components of Z mod q mod Z. Now q mod Z is a group which contain elements of the form a plus z, where this a is in q. So this is the infinite group, but this group is such that each of its elements are of finite order. So if we have an element here, say this quotient p by q plus z here, so this is a, which is a rational number, so it is better to write here p by q. So this is p by q. So one can note here this is an element of q mod z, and if we multiply q here, this becomes p plus z. Now p being an integer, so this p plus z is same as z. So this element over here has order q. Now this is a group, such a group which is infinite, but each of its element is of finite order. Now one can prove that this Zp in infinity, this is isomorphic to the p primary components of q mod z. But to prove this result here is beyond the scope of this lecture, so let us stick to our business. Now one can see over here this g mod pg is not the this null subgroup, because neither g is infinite nor g is the zero group, so this is not equal to 0. So this means that dimension of this g mod pg is 1. Therefore dimension of g mod pg, this is 1, i.e. dg is equal to 1. So this dimension is over some finite field fp. So this is 1. Now let us prove the other direction. So conversely, if dg is equal to 1, then g mod pg is isomorphic to z mod pz. because if this dg is equal to 1, that means dimension of g mod pg over z mod pz is 1, but at the same time dimension of z mod pz over z mod pz, this is also 1. Now any two vector spaces with same dimension, they are isomorphic, so this g mod pg has to be isomorphic to this z mod pz. So g mod pg is isomorphic to z mod pz. Now this group over here is cyclic, so this g mod pg is also cyclic, hence z mod pz, sorry, g mod pg is cyclic. So we have, it is generated, so it is generated by an element, say g mod pg is generated by the element, say z plus pg, because this group has the elements of the form the cosets of pg, so this is the coset of pg in g. So g is given to be non-zero, so if this g is generated by z, then we are done, because we have to prove this g is cyclic. So of course g is non-zero, and if g is the cyclic group generated by z, then we are done, because this is what we have to prove. We have to prove g is cyclic, so we are done. Now z being an element of g, so if this is not true, then z being an element of g, so if then the subgroup generated by this z here, this is a proper subgroup of g. So if this is not true, then this is properly contained in g. So assume, so suppose g is not equal to this thing, then this is a proper subgroup of g. Since z is in g, this is the reason. So this is a proper subgroup of g. Now we are going to use the correspondence theorem. This correspondence, so the correspondence theorem says now z mod pz being a field and this group being isomorphic to g mod pg, one can note here this is also a field. Now if this is a field, so pg will be a maximal idle in g. So the corresponding theorem says that this pg is a maximal subgroup of g. So by a maximal subgroup M of G, we mean, suppose we say M is maximal in G whenever there is a subgroup H such that M is contained in H and H is contained in G, either M is equal to H or H is equal to G. So in that case M is said to be maximal. So then PG is a maximal subgroup of G. So we claim that PG is only maximal subgroup of G. So we claim that PG is the only maximal subgroup of G. This is our claim. Suppose not, I mean there is some other maximal subgroup of G other than this PG. Suppose not, let L be another maximal subgroup of G. So we claim this is another maximal subgroup of G. So if L is maximal, so then G mod L is a field, then G mod L will be a field. So we claim that this G mod L is isomorphic to Z mod PZ. The reason being, so if L is maximal, then G mod L has no proper subgroups by correspondence theorem. So if there is some subgroup of G mod L, so here we are going to use the correspondence theorem. So we are claiming that this G mod L is simple. So because if there is some subgroup, suppose H is a subgroup of G mod L, then that means there exists some subgroup, say K of G, which contain L. But L being maximal, there is no proper subgroup of K which contain L. So this means that G mod L is simple. Now G being simple and abelian, so this must be a group of prime order. This is the this we have proved in the previous lecture. So then so L is maximal subgroup of G, then by invoking correspondence theorem, G mod L is simple. I mean it has no proper subgroup. For if it has a proper subgroup, then G has a proper subgroup which contains L properly, but that is not the case because L is maximal in G. So G is simple. Now G mod L being simple and abelian, its order must be a prime. But G mod L being simple and abelian, we have G mod L. Now L being a maximal subgroup of G, it must be a field. So G mod L being simple and prime, its order must be a prime. G mod L being simple and prime, its order must be a prime number. Prime number. So that means now that prime must be equal to P, because G is given to be P primary. So its order must be a prime number, must be the prime number P. That is G mod L is isomorphic to Z mod PZ. In other words, let us take any element here. For any A plus L in G mod L, so its order must be a prime number, because G mod L is comma P of A plus L, which is equal to, so it must be the identity of this group, that is L, or now this is PA plus L, PA plus L is equal to L, that is PA is in L, because we know that if H is equal to A plus H, this is true if and only if A is in H. So that means PA is in L for all A in G. Note that this A here, this A is an element of G. So this PA is in L for all PA in G. That is PG is contained in L, because this means that now element is over here, these are of the form PA. So now this PA, this is in L, that is why this containment is true. So PA is in L. But this L is given to be a maximal. This PG is given to be maximal in G. That means this PG is equal to L. But PG being maximal in G, we have this PG is equal to L. So this means that there is only one maximal ideal of G. PG is the only maximal subgroup of G. Now if this is the case, so as every proper subgroup is contained in a maximal subgroup, so every proper subgroup of G is contained in PG. So let us write this down as every proper subgroup is contained in now G being a group having this unique maximal subgroup PG, this means every proper subgroup is contained is contained in a maximal subgroup. So this is a result. Every proper subgroup is contained in a maximal subgroup, but in our case G has this unique maximal subgroup. That means every proper subgroup of G is contained in PG. So every proper subgroup of G, every proper subgroup of G is contained in PG. Now if this is the case, then therefore in the beginning we have assumed that this subgroup is a proper subgroup of G. So therefore this proper subgroup Z is also contained in PG. Therefore this subgroup is properly contained in PG. So let us, this Z is contained in PG, so that the generator Z plus PG of ZG is 0. Now if this is contained in PG, that means Z is in PG. Now if this Z is in PG, that using this theorem over here, H is equal to A plus H if and only if A is in H. Now let us go this direction. If A is in H, then H is equal to A plus H. Now this Z is in PG, this implies this Z plus PG is same as PG. So therefore Z is contained in PG. Hence this Z is contained in PG. This implies Z plus PG is same as PG. But we have assumed that this G mod PG is generated by A plus PG. We have this G mod PG is generated by the 0 of this element, that is PG, i.e. G mod PG is 0 because the 0 element of this group is PG, so which is a contradiction, because at the first place we have assumed that this is non-zero cyclic group. It's a contradiction. Hence this Z is not properly contained, but this Z is actually equal to G, as this Z is maximal subgroup of G, i.e. G is cyclic. So this proves this theorem.